seconds. Hi again, welcome to the last talk of the morning session. Our speaker is Vedran Dunjko, Associate Professor at Leiden University, the Netherlands, and he will talk about quantum machine learning beyond quantum kernels and with smaller circuits. Vedran, thanks for coming, and please go ahead.
Thank you very much, Andres. I hope you can all hear me. It's a pleasure to be here, and many thanks to the organizers for the very kind invitation. So today I'm happy to be reporting a couple of new results that we've developed here in Leiden, where we're trying to figure out how to use, let's say, near-term or not far-term quantum computers to do something useful, and it will have to do with quantum machine learning. So before going into the actual details, maybe I want to spend a second or so thinking about why discuss quantum machine learning at all. And it's actually not a new idea. Quantum machine learning is in fact one of the first things we studied in quantum computing already in the early 90s, in part because machine learning can be computationally intensive, right? It has computational bottlenecks that we can identify. For instance, in certain boosting models, we in the end have to solve some kind of a combinatorial optimization problem. And in the early 2000s, people thought that maybe Grover-like speedups or maybe similar to quantum annealing or adiabatic quantum computing speedups, maybe even quadratically speed up the process. And maybe more famously, around 2010s or so, the fact that quantum computers can be used to kind of tackle certain types of linear algebraic problems in some sense more efficiently. This could be an entry point where a lot of big data quantum machine learning could be actually executed. So this was all about resolving computational bottlenecks in machine learning issues. But what I want to talk about today is driven by different moments. Let's go back to 2019, where we had this now very famous result of Google, which claimed quantum computational supremacy. So it can be argued that some kinds of new quantum computers, right, genuine quantum computers, have arrived, but of course they're in fact very different than the ones that we studied for 30 or more years in theory, right? They're limited in size, they're limited in architecture, they're extremely noisy and error prone, and in essence this means that we don't have good ways to program them. None of the results that we studied for 30 or more years really apply to the devices that we have, while at the same time we have theoretical evidence, a reason to believe that they do have certain computational capacities beyond classical, right? And now it's the question of how to harness this to use something useful, and that's where quantum machine learning comes as an interesting possibility, because we somehow get the most we can out of the device without really thinking or worrying about as to what it's actually doing, right? Machine learning is all about getting machines to do things which are useful without explicit programming. So this is the kind of quantum machine learning I want to discuss today. We're not chasing speedups. We're going to be doing machine learning in a different way, and then hopefully be able to show that there's something interesting and useful happening there. So the basic object that we discuss is so-called parametrized quantum circuit, sometimes known as a variational quantum circuit, depicted here, where we imagine a register of a certain number of qubits and a sequence of gates which are predefined, or rather the architecture of the circuit is predefined and fixed. So in conventional algorithms, the algorithm itself specifies which gates are applied in what sequence, and the depth of the circuit, width, and other parameters depend on instance size, and it's kind of fixed and designed by the algorithm. But here we turn the story around. We say, no, we're going to first fix the architecture. The depth is going to be fixed, the width is going to be fixed, and the gates are going to have certain parameters which we can tune. Right, so there are tunable parameters associated with each gate. Like, think of it as an angle of rotation, if you will, or for the physicist, the duration of a field, duration of time that the field is applied to a system. And now this entire thing, whatever it is, in the end manifests or rather implements a function, right? A function which has certain parameters which correspond to the input. Let's call them x. Certain parameters which specify a particular function in the function family. I call them theta. And the output is governed by the laws of quantum mechanics, or rather the Born rule, in this particular case. So this is a physical way of implementing a function family. And the moment when we have function families, we can start thinking about machine learning. So we would call this a parametrized function, or maybe a hypothesis class, or more broadly, a machine learning model. And if you look at it, it has a striking resemblance to a much more famous class of parametrized functions, which are neural networks, which also have layers that we can talk about, which also have certain parameters associated to, well, both the nodes and the connections between the nodes. They have a width, and they implement some kind of a classical function, right? An input-output relation. And because of this structural resemblance, the quantum analog is sometimes called a quantum neural network, even though from the mathematical perspective, the types of functions they implement are very different. And this is exactly the reason why we want to consider them at all. So for better or for worse, people in my community for the last few years, what we've been really doing is taking a machine learning model, a classical one, we would find the neural network inside, kick it out, and put in a quantum neural network, in essence, hope for the best, right? This is the kind of thing we do. Maybe I'm oversimplifying things a tad bit. And it's an absolutely fair question to ask, okay, why on earth would you do that? Right? Why would you want to substitute the neural network with a quantum model? And a one-line reason is because models matter, right? I mean, the success, the empirical success, real-world success of machine learning is pretty much driven by deep neural networks, which are certainly not fully understood from a theoretical point of view. And at the time when we started realizing just how powerful and useful they are, we had nothing but negative results about whether they should be used or not, right? So interesting, powerful models can bring about interesting, powerful results, even if we don't fully understand them theoretically, or that's our hope. So once we accept that this is what we want to do, kind of two classes of questions pop up that people like asking. I'm going to call the first class a bit more pragmatic, let's say, so where the question would be, can we actually get these things to work as a machine learning system? I mean, is it actually robust to noise? Can we really run it on a device, even if the gates are aligned with the device itself? Can we actually train them? And in fact, we now know that in general, training of these models is actually very, very challenging. And there's going to be a beautiful talk by Maria Kiferova today later, telling you about new ideas how to actually resolve that issue. But today I want to ask the, let's say, more theoretical set of questions, which are along the lines of, should we actually get it to work, right? Is there any good reason to believe that these models do anything interesting? And here we could be worrying about whether we can characterize the generalization performance, so theoretical bounds, statements which tell us how well our machine learning model will perform beyond the training set, right? So we see some performance in the training set, but we want to have guarantees that it's not going to be, let's say, much worse when we put in a data point which was not in the training set. Then we would like to know whether it's possible to have a quantum advantage. Is there a learning problem that actually benefits from these types of models? And here we have certain examples where this is the case, albeit quite contrived and not really related to real-world applications. But also we can ask about what kinds of types there are. What's the expressivity? What can they do? What do they look like? And in this domain, nowadays we kind of have three main classes of models, let's say. One I will call an explicit model. The details are not relevant, but for the experts, it is manifested by having the first part of the circuit depend on data alone, and the second part of the circuit be independent from data, but otherwise trainable. This gives a certain mathematical structure, which makes them linear classifiers and related to so-called support vector machines. Then a derived version are so-called kernels, which are super famous and for good reason, and I'll talk about them more in a second. And then finally, we have data reuploading models, which are sort of the most general thing you can do where you have no a priori restrictions on how the circuit is built. And now we have studied these models in great detail. We understand quite a few things about them, but of course, far from everything that we need to know. But in particular, these models, these implicit models, these particular ones that I'm pointing at with my mouse, they're very, very convenient because they relate quantum information processing to classical kernel methods, which are really well understood. And in fact, they're quite powerful. So it has been suggested that perhaps these are the only things that we should really worry about in the quantum case. So this slide is actually quite math heavy, and for most, it's not really important to understand all the details. But I want to highlight the notion of a feature space. So one of the key ideas behind explicit and implicit models is the use of a certain mapping which takes your data, and by data here, what I really mean is n-dimensional vectors. So you can think of an image, a picture, simply being as a long vector of values encoding the color of each pixel, right? So it's a real valued n-dimensional vector, which we map into an even higher dimensional space where the data becomes easier to analyze and easier to separate and classify. So this higher dimensional space is called the feature space. And this is a very powerful tool. You can show that this can, in principle, classify whatever you want. But there's, of course, the painful fact that you have to work in these even higher dimensional spaces. Now, of course, in the quantum case, the idea was that to use the Hilbert space of the physical system as the feature space, but it's still an exponentially large thing that it's kind of awkward. But here, a piece of mathematics called the reconstructing kernel Hilbert space and a so-called representative theorem come to the rescue, which say that you can kind of work without ever actually dealing with the feature space explicitly, as long as you can compute the inner products of your data points, which you will get had you mapped your data points into this higher dimensional space. So we avoid a lot of nasty mathematics, and things become much simpler, both in training and theoretically. While at the same time, there's the representative theorem, which kind of tells you that the types of models that you get this way are in some sense the best ones. They're the ones you would obtain anyway if you had to train your explicit model with respect to the loss function and well, a wide class of meaningful regularization functions which are going to prevent overfitting. So they're convenient and extremely powerful, right? So one can ask, is this really the thing that we want? I mean, is maybe all of quantum machine learning about kernels? And if it is this bad news or good news? And in fact, it might be bad news. So there's this beautiful paper by the Google team, Power of Data and Quantum Machine Learning, which analyzes quantum kernel methods and identifies a heuristic, a thing that you can measure and evaluate in your data set, which gives indications whether a quantum model will actually do better than a classical kernel. And identifies that there's actually a very narrow region of parameters where you could even hope to see a quantum advantage in learning. So that feels like a bit of bad news, right? So we were a bit bothered by this. We were really wondering whether these kernels are really all there is, or whether there are reasons to consider explicit models still. And we were wondering where data reuploading models fit, which are not directly related to either explicit or implicit models. And this brings me sort of to the one slide of the main sequence of results that we had in this paper here, which provides some first answers to these questions. And the slide is this one. So number one, I didn't comment this in much detail, but by construction, these data reuploading models contain explicit models as a special case. So they're more general, right? So the question is, are they really more general, or do they just look more general? And we prove that you can always map any data reuploading model into just an explicit model, where the price you pay is that you have to use more qubits. How many more qubits depends on the number of layers that your data reuploading model has. So this is kind of telling you that from a very coarse-grained theoretical perspective, the only thing we really need to worry about are linear models. They're going to tell us everything that can possibly happen in quantum machine learning. At the same time, we've also analyzed this discrepancy between kernel methods and explicit models. And we've shown that even though kernel methods will provide the best function with respect to certain regularization parameters in the data set, they can also dramatically overfit. So in particular, we provide a counterexample to this, some of the results of that beautiful paper of Google that I mentioned, where they've shown that classical kernels are much better than quantum and anything else. We actually showed that this is not universally the case, that sometimes you really need to work with explicit models. And then in the third result, we kind of point out that all of these things in the end give you a big picture, but if you care about fine-grained properties, and if you have to make informed decision on what to really use, then you cannot drop any model. So specifically, we construct learning problems where the data reuploading model, which I briefly mentioned, can be represented in explicit model, but the data reuploading model can learn this problem using logarithmically many examples in the dimension, using just a single qubit computation. And yes, you can solve it with an explicit model, but for that one, we prove needs to utilize at least d qubits. but it's also efficient in terms of number of examples that you need. However, if you want to do this with an implicit model, then you need an exponential amount of data. So it is ultimately inefficient in terms of sample complexity, which is sort of an interesting result. So this fact that the number of qubits that you really need can differ and the depth differs, this all means that from a practical point of view, if you want to solve a particular problem on a particular device, you really have to consider the world of all possible circuits, and none of them are a priori going to be better for all problems. So that's what I want to highlight at this sort of half point of the talk, that there's no one-size-fits-all solution for quantum machine learning. And perhaps this is obvious to many. Machine learning is messy, and there's no one-size-fits-all solution for machine learning in general. So why would there be for quantum machine learning? But we just can exemplify this by showing the differences between individual models. So the challenges in the field, of course, are, well, ideally, we would like to prove as much as possible theoretically to show that there are, for instance, relevant problems for which you can prove separations. Maybe problems in highly correlated physics, many-body physics, something like this, or maybe high-energy physics. But at the same time, we know that in machine learning, I mean, we really need real-world experiments, right? Machine learning classically is successful not because of theory. In some sense, it's successful despite the theory which predicts that deep models should actually not function very well. So we need real-world experiments, right? Maybe they're guided by theory. And here's, of course, where we hit the second bottleneck, and that's that, on one hand, we cannot simulate big quantum computers because they're quantum, and that's why we want to have quantum computers. While at the same time, the quantum computers that we do have are actually comparatively small for the types of places where you would want to have a powerful machine learning model. And machine learning becomes really interested with high dimensions and large data sets. Otherwise, we have very effective simple solutions most of the time. But we cannot say much about what quantum computing could do in this particular case, right? The devices are simply too small. So we were thinking about, mitigating this a little bit. So asking whether we could tackle somehow larger problems than we have than the size of device that are available, while still, applying it to something which is comparatively large. Maybe not use just full-blown quantum computing all along, maybe doing something hybrid, but still providing some indication of what would happen if we had a larger quantum computer. So what I want to do is I want to mimic quantum machine learning, which uses a large quantum circuit, but using smaller quantum circuits. The word mimic here is carefully chosen because I really don't mean simulate, and I really don't mean approximate, because those terms are have mathematical meaning. Here, I will not be able to prove too much about whether they do the same thing or not, but they're going to be related in a way which is going to become clear. So the basic starting point is the fact that we've known for a long time that if I had access to a smaller quantum computer than my circuit, I can still use this quantum computer, the smaller one, to evaluate the large quantum computer more efficiently than just simulating everything classically. So the basic observation is if I have a quantum computer of, let's say, n qubits, but the first n half qubits do not communicate with the second n half qubits, so there's no entangling gate across the cut, then I can evaluate the two circuits independently and somehow efficiently combine the results. Effectively, it's going to be a product of the outcomes. And if I do have a CNOT or an entangling gate in between, well, a mathematical trick allows me to represent such things as sums of 2 or 4 single qubit gates. Now, sums, of course, don't have really meaning in terms of circuit evaluation, but I can mathematically write it down. And what this means is that I can actually simulate or compute the output of the larger circuit by simulating many runs of smaller circuits. How many? Well, exponentially many the number of CNOTs that I cut. And of course, this is the point where the thing becomes inefficient. There's a combinatorial blow-up, and it feels like this is sort of a dead-in-the-water idea. But we can ask, do I really care about all the terms in this exponential sum? So maybe for the experts, just to point out this product here in the function that I'm computing, this is calls to k subcircuits, smaller circuits, assuming that I have k-1 cuts. And this sum here is over all the possible terms that I will get from the decomposition of CNOTs. Right? This is just technical detail. Anyway, so my question is, do all of these terms actually contribute? Right? Maybe they don't. Maybe only some of them contribute, and maybe I can actually simulate this much more efficiently than I would hope, than I would expect. But of course, I need to know which ones, right? And this is now a combinatorial problem, right? I would have to select the correct subset, and this is going to be, in general, NP hard. But the fact is that all of these sub-circuits which appear in the sum, in this exponentially many summing terms, they're actually very much alike. They differ in 1 or 2 gates, depending on which CNOT we've been cutting. That also means that I can actually, instead of having these particular fixed gates which come from CNOTs, I can have them parametrized. So I'm adding parameters to the model. And I'm in the right setting of those parameters is going to enable me to mimic any one of these exponentially many terms. So now what I can do, I can actually fix the number of terms that I want to consider to some constant numbers. It's going to be a model hyperparameter. And I'll have the property that for the right setting of these additional parameters that I've added, I can mimic any subset of this exponential large summation. So this is, mathematically speaking, a relaxation of the combinatorial optimization problem that I had a second ago, which dealt with selecting the most important terms. And one of the properties that you immediately get is that this model, which is restricted in the number of terms that I'm considering, but more general in the number of parameters that these terms have, this model will contain all the best possible solutions I could have gotten by taking a smaller subset of the terms in the sum. So it's containing interesting solutions if there are interesting solutions which involve fewer terms. At the same time, the model that I got now no longer comes from a quantum circuit. I've left the structure of quantum circuits. I'm something more general than that. And in fact, in order to mimic this now classical quantum hybrid, I would require a much larger quantum computer. So now we should be really talking about this not being an approximation of the bigger quantum computer, but rather something which is inspired by a bigger quantum circuit, but otherwise is a new model. But the fun fact is that we can analyze it. We can do most of the analysis that were done for quantum circuits for this model as well, and show that, for instance, even though we've added more parameters to the model, it doesn't really hurt its generalization bounds compared to the full-blown quantum model, which is also bad news because it does contain significantly fewer terms in the sum, which should be visible in bounds going down. Actually, it's performing better. So for this, it's clear that we need, well, new quantum-specific approaches for finding these generalization bounds, and that's something that we've been working on quite a lot recently. Separately, because of this additional explicit structure of the functions, we might have a new class of algorithms which are somehow tailored to these types of functions, which don't suffer from the same, from barren plateaus to the same extent as the full large quantum circuit would. It will suffer at least as much as the smaller circuits would, but then again, I could be cutting my large circuit in many small chunks, and this could in fact be much more tractable than the large quantum computer. So in essence, this gives me a convenient framework for thinking about further hybridization, because now I have meaning to these things. I know that they correspond to cut of a large circuit, but I can start adding classical parts, classical neural networks to my model, and still do this type of an analysis of the performance of the model. Now, this is the theory part. Now, we've, of course, empirically tested it on perhaps the most boring data set we could have, but it's the standard one. It's the MNIST, the digits, which we fed without further dimensionality reduction, 64-dimensional problem, but without further dimensionality reduction. And we've shown that it kind of works really well, even with very few terms, which is, of course, much more than we could fit in a real quantum computer. So this suggests that adding terms doesn't really matter for these types of data sets. But then we've also generated data sets which use a full-blown quantum circuit, so a large quantum computer which has many signals that you would have to cut. And there we see clearly that adding terms directly improves the performance of the model. So it just goes to show that this is a hyperparameter that can be used to decrease or increase the expressive power of a model, which could allow us to then do things like structural risk minimization. So get our model to perform well without bad generalization bounds on simple systems. And if the systems demand it, then we tune that parameter up. Everything becomes more expensive, but it can capture more complicated correlations, like full-blown quantum correlations. And that brings me to the end of the theory part. And now, given that this meeting here is not just for science, I was also asked to reflect for a second on how does this mix and match with industry, right?
Vedran, sorry, you have 1 minute plus 5 minutes for questions.
Yeah, I'm done in 1 minute.
Thanks.
I'll be done in 1 minute. Thank you. So the take-home message that I want to make along this route is that down the line, quantum machine learning is going to, whether it's successful or not, is going to heavily depend on what we apply it to, right? It's not going to be a universal solution to anything. And then the question becomes, what do we apply it to? And I mean, do we apply it to images, to voice, to signal processing? We don't know. And we will not be able to know until we try, right? So we need case studies, and perhaps we need them now, right? And this is where we go in the applied quantum algorithms group when we collaborate with our industrial partners. We're really doing quantum computational discovery, right? We're testing out what quantum computers can do on particular case studies. Here are some examples with total energies. We're studying mesh segmentation with Shell, where, like many other groups, we're studying quantum chemistry problems. But we're also doing other things like studying reinforcement learning for driving problems and related things. So the key point for us there is to generate know-how, right? To generate know-how and experience in what kinds of quantum machine learning models do well in what settings, and how does it scale, to have some indication where we could hope for real-world advantages. I mean, constant improvement advantages, perhaps. Maybe we're not talking about things that are even definable in a pure mathematical way. But for that, we need interesting questions. And that's where industry comes, and industry gets know-how and ideas of how things might develop in the next 5 to 10 years. And that brings us to the end of the talk. And I want to thank all the collaborators and students who worked on these works. I will provide the slides to everyone who's interested. We have everything implemented in TensorFlow, so you can play with it. And I thank you very much for your attention.
Thank you very much, Vedran, for the nice talk and for this outlook to the industry sector as well.
Yeah,
we have a number of questions in the chat. We have time maybe for 2 or 3 of them. First one from Aritra Sharkar. In classical machine learning, a major problem is understanding the trained parameters in the neural network. In variational quantum computing, won't this be worse, as we don't even have access to the intermediate states?
Probably. So I mean, I would have to ask a sub question whether the question is about interpretability or
explainability of the trained parameters for critical decisions.
Yeah. So there are in fact tools involving estimations of the Hessian. So there are classical methods for somehow understanding the significance of individual parameters that are applicable also to the quantum models. Indeed, it's going to be more difficult in general because we cannot access the intermediate state. That's absolutely correct. But it's not the case that none of the techniques apply. So in essence, you're going to have to do various measurements as you perturb the parameters and analyze what happens with the second derivatives. That's one of the things that can be done. That's all I can say for the moment.
Thank you. Second one from Zoltán Cimborás. What do you think? Would you be able to use such a divide and conquer hybrid model for other applications of variational quantum circuits, say VQEs?
So I'm scared of saying anything about VQEs if we're talking about problems of quantum chemistry, because these things, have a lot of side information, right? These are Hamiltonians with symmetries, and we know a lot about them. And it's not the case that I'm throwing an architecture that I don't know how to say in any particular way. So there, I would say, if you want to chop things up, probably study the system, and probably classical people have done it implicitly anyway. Like if you think about the QMMM methods, quantum mechanics, molecular mechanics, they kind of identify the sites which can be treated classically and which we treated quantumly. So this is related in spirit. But I have the feeling that for this cutting business, for the chemistry case, that you need to talk to chemists a lot, and then you can have meaningful solutions. For machine learning, there's no such thing, right? There's much less that we know, so it's okay to go into it more or less blindly, I would say.
Thank you. So to be able to provide some lunchtime for everybody, let's conclude here. Thank you very much, Vedran, and also thank for all the speakers
for invitation
of the morning session. And so I think we have now 18 minutes of a break, a lunch break, and then we will reconvene again at 1:45 Central European Summer Time. Thanks a lot, and see you later then.
You take care.
Bye.